All right, this is problem number 4 from chapter 6 of the Halliday and Resnick book. We've got this pig that's going down a slide. It tells us the slide is inclined at 35 degrees. And it tells us that the time that it takes him to slide down the slide, so the time to go down the slide with friction is exactly twice the time that it would take the pig to go down the slide if there was no friction, right? Okay. And so it wants to know the coefficient of kinetic friction between the pig and the slide. So we're looking for mu k. All right, so let's do this. We don't know a ton about sort of what's going on here, but we can certainly find the acceleration of the pig if there's no friction, right? Because look, if there's no friction, then the only force on the pig is going to be our parallel component of gravity, right? And so the acceleration with no friction would just be the net force, if there's no friction, divided by the mass of the pig, right? Well, the net force then would just be our Fg parallel divided by the mass of the pig. And Fg parallel is just Fg, or mg, times the sine of theta divided by the mass. So g sine theta. So that's our acceleration if there was no friction. So what I want to do then is see if I can use this idea here to figure out what's the acceleration of the pig with friction. Okay? So here's the deal. I know that whether there's friction or not, my initial velocity is going to be 0, right? So let's do this. Let me clear up some space on the board here. Okay, and so the equation that I'm thinking about is this guy right here. I know that displacement is 1/2 at squared plus VOT, right? But since my initial velocity is 0, this whole thing just goes away, right? So let's rearrange this thing for acceleration. So the acceleration of the pig with friction, let's rearrange this. Sorry. So whether there's friction or not, our displacement is the same, right? So let's rearrange this equation for acceleration. So the acceleration of the pig is going to be 2 times our displacement divided by t squared, right? So specifically, the acceleration with friction is going to be 2 times the displacement divided by the time with friction squared. Okay? Well, look, we know, though, that the time with friction is equal to 2 times the time with no friction, right? So this becomes 2 times displacement divided by 2 times the time with no friction squared, which is just 2 times the displacement over the time with no friction squared times 1/2 squared, right? Basically, I just pulled out this 2 squared, okay? But so then notice, this guy right here, well, that's our expression again for acceleration, but this time it's the acceleration with no friction. So this is the acceleration with no friction times 1/2 squared, or in English, it's the acceleration with no friction divided by 4. Okay? That seems like it might be useful information. Okay, so I just moved this stuff up, up here. All right, so now let's take a look at what's going on. So what we just discovered is this, that the acceleration of the pig is equal to the acceleration with no friction over 4. So that's this over 4. So it's g sine theta over 4. So let's take a look. Here's our pig. So we've got Fg parallel pulling him down, force of kinetic friction pulling him up. So my net force in this example is Fg parallel minus Fk, which is mg sine theta minus our coefficient of kinetic friction times our normal force, right? But our normal force, well, that's just mg cosine theta, right? So our net force now is mg sine theta minus the coefficient times mg cosine theta, right? Let's see. And so if I divide that whole thing by mass, that should give me my acceleration, right? Okay, so we just divided everything here by m, so these m's are going to cancel out, and this whole mess here equals g sine theta over 4. The equation I'm looking at now is this, g sine theta minus mu k times g cosine theta equals g sine theta over 4, right? So the next thing I notice is that everything here is divisible by g. So let's just go ahead and divide everything by g. These guys cancel out. And then I'm going to multiply everything through by 4 to get rid of this fraction here. So here's what I'm left with. 4 sine theta minus 4 mu k cosine theta equals sine theta, right? So now we're just solving for mu k, and we know what theta is, so really here it's just kind of plug and chug. But let's finish it up. So let's see. Let's subtract 4 sine theta from both sides. So you get negative 4 mu k cosine theta equals, over here I've got sine theta, and I'm going to subtract 4 sine theta, so I'm going to get negative 3 sine theta. So then just divide both sides by negative 4 mu k. Oh, and by cosine theta. No, what am I doing? Rewind. I'm trying to solve for mu k. So let's divide by negative 4 cosine theta. So the cosine theta is canceled, the negative 4 cancels, so you get mu k equals 3/4, and then sine theta over cosine theta is just tan theta. So for us, that's 3/4 times the tangent of 35 degrees. Okay, and that should give you your answer.